The mid-ordinate rule is used to approximate the area under the graph between two limits, like the example. Why do we use it when we can integrate? Well, a function like this, yes, we can integrate, but sometimes you'll come across a function that you can't. Well, maybe you've got a graph that you need to know the area under it, but you don't know the function. And so the mid-ordinate rule is a good way of approximating the area. We do this by splitting the area into rectangles, finding the area of the rectangle, and then using that to approximate the total area that we want to know. So the step is to split our area into strips. Once we've done that, we find the mid-ordinate of each strip. So we find the mid-x ordinate, which gives us where the base of the dotted line is, and then the corresponding y-ordinate gives us what's going to be the height of the rectangle in each strip. There's our first rectangle. You can see the height of the rectangle is the same as the y value, or the y-ordinate, and the base of the rectangle is the same as the width of the strip. Same for all the strips. Now, what we can see is that for each strip, part of the area in the rectangle is not under the graph. Same for each rectangle. But this is compensated by the fact that there's also some area that's under the graph but isn't included in the rectangle for each strip. And so this minimizes the error and gives us a good approximation. Okay, let's use this rule to approximate the area under the graph of the function that we've got in the example. The step is to calculate strip width. Now, you can look at the diagram and you can see the width of the strips, they're just one. Alternatively, we can use this formula to calculate the strip width. So A is the lower limit and B is the upper limit. And we can find the difference between them and divide by the number of strips we want. So we've got the calculation. As we know, the total width is 3. We divide it by, we want 3 strips, so 3 divided by 3, and the strip width is 1. Next step, we want to calculate the x mid-ordinates. So let's think about the first one. To get to the first one, we need the lower value, a, which is -1. Then we want to add on the width of half the strip, so that's 0.5. That gives us our first ordinate of -0.5. We can draw out a table of these. We're working out the x ordinate at the moment, and then we'll work out the y ordinates. So we've got our first one already, -0.5. And the next one is the strip of one width above that. So the strip of the width is 1, so -0.5, add on 1. Add on 1 again for the next one. Once we've got our x ordinates, we can calculate our y ordinates using our function x squared plus 1. So first of all, -0.5 squared plus 1, and the same for each x ordinate. Now we need to go on and find the area of the rectangles. So we know the width is 1, and we've found the height of each now. And here's a general formula for finding the area of each rectangle. Looks a bit involved. We're going to simplify it, don't worry. But if you look at each pair of brackets, what we've got there is b minus a over n, that's the strip width. And we're multiplying it by the y ordinate, the height of each rectangle. And we do this and find the sum of the areas of however many rectangles there are. In our example, we've just got 3, nice and simple. We can simplify the formula for area though by taking out a factor of the width. It means the area is simply the width times the sum of the heights, the sum of the y ordinates. This is a formula that you get in the formula booklet. This is what it looks like in the formula booklet. A little bit different, but virtually the same. So once we've got our y ordinates and we know the width of the strips, we can simply substitute these values into the formula. So for our area, the width is 1, so it's 1 times the sum of the y values. Our area is 5.75. Final answer. Why don't we have a quick think about how accurate our approximation is? What's the relative error? Well, we know what our area is using the mid-ordinate rule. We know it's an approximation. In this case, we can integrate to find the exact area. So you can either integrate by hand or you can use a calculator, but the answer is 6 square units. So we can see it's a value of 0.25 out, but our relative error we find by dividing the actual error by the true value, then multiply by 100 to turn it into a percentage. That's our calculation, and our relative error is 4.16%. About a harder example. We've got a function here that we can't just integrate, and we're told that we want to use 10 rectangles to approximate the area. The more rectangles we use, the more accurate it will be. And we've got our formula there we're going to use. We could draw the graph, could sketch the graph, but we don't need to. We can just work out our values and use the formula. First step again, with the strip, the difference between the limits divided by the number of strips or rectangles we're using. Gives us a width strip of pi by 10. Next step, we're going to do our table of values. We'll calculate the x ordinates, but the first step is to find the initial x ordinate. So our lower limit is minus pi by 2. Half the strip width is pi by 20. Gives us our first x ordinate of minus 9 pi by 20. So let's put in the x ordinate in our table first. So each time we're increasing by 1 whole strip width to go between the mid-ordinates. So our width strip is pi by 10, minus 9 pi by 20, add on pi by 10, or 2 pi by 20, to minus 7 pi by 20. Add on 2 pi by 20, minus 5 pi by 20, and so on. We're doing 10 rectangles, 10 strips, so we're going to have 10 mid-ordinates. And we know we're finished when we get very close to our upper limit of pi by 2. We can then use the function to calculate our y mid-ordinates. Now we've got 10 to calculate here, and at this point it might be tempting to think, oh, I'm just pushing the buttons on the calculator to work these out, but there's a lot of calculations. It's not too involved a function, but we still need to be careful when we're working out our values. I'm working out values to 4 decimal places. If you want an answer accurate to 4 dp, then of course you need your working to be more accurate than that. We're going to work out our values one by one. Or you might want to use the memory function on your calculator to add up the exact values as you go. And as you work out each value, think about how you're going to minimize the keystrokes on your calculator, because there is a lot of calculations to be done. Lastly, even before we start, we need to notice that we're working out trig values here, and we need to think about what are our units. Here it's pi by 2 or minus 9 pi by 20, minus 7 pi by 20. We're working in radians, so don't work this through and then suddenly realise that you're working in degrees. So calculate your values. Interesting to note on this one that because of sine being an odd function, that our values of pi by 20 and minus pi by 20, they're actually the same. They mirror each other. 3 pi by 20 and minus 3 pi by 20, they're the same, and so on. Okay, so now we can substitute our values into the formula. There's the width strip and the sum of the heights of the rectangles, or the sum of the y ordinates, and there's our value.